Welcome student, paper CH6502 in Organic Chemistry Unit 1A, term symbol for energy levels of an atom. This is the second part, term symbol 2. In part 1 we have discussed what is term symbol, what is the importance of term symbol, what are microstate, how to calculate microstate for different atom and ions, how we can assign the term symbol to particular microstate. This kind of information we have collected in a term symbol part 1. This is term symbol 2. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Well, today we are going to discuss regarding Hund's rule to decide the ground state term symbol. Then we're going to discuss how to arrange using this Hund's rule, how to arrange the specific term symbol for particular atom or ions in the increasing order of their energy, and identify the ground state term symbol for that particular atom or ion. Then we are going to discuss regarding the calculation of the ground state term for particular atom or ion. So there are certain steps involved in the calculation or identification of the ground state term symbol for particular atom or ion. And then we're going to discuss regarding two important theory, that is pigeonhole diagram, pigeonhole concept for P2 configuration and D2 configuration. So this much is there in this part of term symbol unit 1A. Let's begin with Hund's rule to decide the ground state term symbol. Rule 1, that is about a maximum S value. Here S stands for, let me tell you, S, which is a capital S. You can see here that capital S stands for resultant spin angular moment quantum number, and that is obtained from the spin multiplicity of the specific microstate. So if we want to arrange the microstate in their increasing order of energy, we need to find out the maximum spin multiplicity value for that specific microstate or specific term symbol. If that particular term symbol have maximum value of this spin multiplicity, will gives us lower energy high stability, and a lower value of spin multiplicity will gives higher energy low stability, and that way we can arrange the microstate in a different energy levels. The term containing the maximum value of S, that is a spin multiplicity, is considered as ground state. So the terms having maximum spin multiplicity is considered more stable term, and therefore ground state has maximum unpaired electrons. Second rule, that is about maximum value of capital L. That capital L, as you know, is a resultant orbital angular moment quantum number. Please mark my words, capital L known as a resultant orbital angular moment quantum number. And the maximum value of this L, that term have lower energy high stability, and lower value of this resultant orbital angular moment quantum number have high energy less stability. So this can help us when the term having similar spin multiplicity, we can take use of this second rule, that is maximum value of L. That will, if the spin multiplicity is similar, we cannot bifurcate the terms or microstate into different energy level. So there, this maximum value of L help us to arrange those same spin multiplicity containing microstate into different energy level. How it is, let's see. If the spin multiplicity of more than one term is equal, then the term having higher value of capital L, that is resultant orbital angular moment quantum number L, is considered more stable term. Say for example, we have triplet S and triplet D. So here spin multiplicity is similar, but S is having L is equal to 0, while D is having L is equal to 2. That means maximum value of D, that means triplet D is going to have more stability. So that way we can bifurcate the same spin multiplicity containing terms into different energy level. Now here the spin multiplicity is similar and even the value of L similar. That means similar term is there. Triplet P. But one is triplet P2, the other is triplet P1, and we want to arrange them in a different energy order. Then rule 1 will not going to help us. Rule 2 is not going to help us as spin multiplicity is similar, as terms are similar P and P. So there's rule 3 can be applied, and that is the value of J. And as you know, J is a resultant spin orbital angular moment quantum number. I repeat again, J is a resultant spin orbital angular moment quantum number. So that value can help us to arrange those microstate where spin multiplicity is similar, at the same time terms are similar as well. That means where these two rules fails to explain the energy splitting or energy difference in the term symbol or microstate, their rule 3 can help us. How it is, let's see. If the subcell is less than half filled, then the more lower the value of J, that is a resultant spin orbital angular moment quantum number, gives more stable arrangement. And if the subcell is more than halfly filled, then maximum value of J gives stable arrangement. Here we are discussing this Hund's rule in the example of P2 configuration. So when we consider this 3 rule for P2 configuration, and if we have triplet P1, triplet P2 and triplet P0, that means triplet spin multiplicity is similar, P, that is value of L is similar. So rule 1 and 2 we cannot use here, but we can use the value of J. Now for P2 configuration subcell is less than half filled. So for that, lower the value of J, that means triplet P0 gives more stable arrangement compared to triplet P1 and triplet P2. So that way we can take help of this rule 3. Okay. Next, in this explanation of rule 1, 2 and 3 to decide the ground state term symbol using Hund's rule 1, 2 and 3, let's take one example for that. P2 configuration, for example, we are taking for this, having different terms. Here you can see the different terms associated with P2 configuration: triplet P2, triplet P1, triplet P0, singlet D2 and singlet S0. Now here one spin multiplicity set is triplet and the other spin multiplicity set is singlet. So we can apply first rule there. First rule, that is the maximum value of spin orbital angular moment quantum number capital S. And when we apply this maximum value of S among these above terms, the one which have maximum value of spin multiplicity, that is triplet compared to singlet, has more stability. That means this set triplet P2, triplet P1 and triplet P0 has more stability, lower energy compared to singlet D to singlet S2, S0. While the terms having lower spin multiplicity like singlet D and singlet S remains in excited state, means in higher energy and low stability. Now here you can see that spin multiplicity is similar and value of P as the same time value of D and value of S are different. So we can apply rule 2, that is of maximum L. So between this singlet S and singlet D, we have two different value of resultant orbital angular moment quantum number L. For singlet S, the value of L is 0, and for singlet D, the value of L is equal to 2. So here maximum value of L gives more stability. That means singlet D gives more stability compared to singlet S. So here singlet D2 is considered more stable compared to singlet S0 using this second rule, that is of maximum resultant orbital angular moment quantum number L value will decide that. Now as per rule 3, the value of J, triplet P2, triplet P1, triplet P0, all the three set are having triplet, 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 that means spin multiplicity similar, and PPP means value of L is similar. So rule 1 and rule 2 cannot be applicable to bifurcate the energy ordering of this set, and for that we can take help of rule 3, that is the value of J. What is J? As you know, it's a spin orbital angular moment quantum number. So we will get the value of J, and there is rule for J, that if the subcell is less than halfly filled, here you can see that P2 configuration. For P configuration, if 3 electrons are there, it is halfly filled, and 6 electrons are there, then it is completely filled. But here P is having only 2 electron, P2 configuration, so it is less than halfly filled. So for that, lower value of J should be considered. So for triplet P terms split into 3 energy levels, as you know, triplet P2, triplet P1 and triplet P0, and in the case of P2 configuration, which is less than halfly filled, as already I have explained you, so lowest value of J gives more stable and lowest energy. Here the lowest value of J is 0. So this triplet P0 is lower energy, then triplet P1 is little higher energy, and then triplet P2 is even more higher in energy. So that way we can bifurcate this set of term symbol into different energy level. So the energy order in the terms for P2 configuration should be given as singlet S0, maximum energy, lowest stability, then lower energy is the singlet D2, then lower energy is the triplet P2, then lower energy is a triplet P1, and lowest energy is of a triplet P0. That means triplet P0 for P2 configuration should be considered as ground state term symbol. So here we can decide the ground state term symbol using this rule 1, 2 and 3 of Hund's rule to decide the ground state term symbol for P2 configuration, and P2 configuration is the configuration of carbon atom. So for carbon atom we can say that triplet P0 would be the ground state term symbol for carbon element. Now here the flow chart is given for this P2 configuration. We're going to apply battery level is low. Okay, P2 configuration, we're going to apply the rule first, that is the rule of maximum S, and using this rule we can arrange this singlet in higher energy level and triplets are in the lower energy level. So this rule first of maximum S help us to arrange the singlet into higher energy level and triplets into lower energy level. Now here singlet is a similar spin multiplicity, so rule first will not applicable for this. So to bifurcate the energy ordering of these two, we can take help of rule 2, that is rule 2 that is of maximum value of L. So for maximum value of L, we can split this energy microstate into 2 energy level, because S for symbol S, the value of L is 0, and for D the value of L is equal to 2. That means maximum value of L is equal to 2 is for D term, and therefore D term is having lower energy, more stability, while S term is having higher energy, low stability. So that way we can bifurcate these two into these two energy level. Singlet D2 is lower energetic, singlet S0 is higher energetic. Now here you can see spin multiplicity are similar, triplet, 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 and even the terms are similar, P, P and P. So rule 1, that is of maximum S, and rule 2 of maximum L cannot be applicable to split these two into 3 energy ordering. For that we can take help of rule J, and for J, because P2 configuration is less than halfly filled, lower value of J gives more stability. So we can arrange this according to the value of J, 2, 1 and 0. We can arrange in this energy ordering. That means triplet P2 is higher energetic, triplet P1 is lower energetic, and triplet P0 is the lowest energetic. Hence, it is the ground state term symbol for P2 configuration. It is the ground state term symbol for carbon element as well. Now here I am going to give you for self-study for D2 configuration. And as you know, for D2 configuration, we have following possible terms, that is singlet G4, triplet F4, triplet F3, triplet F2, singlet D2, triplet P2, triplet P1, triplet P0 and singlet S0. Now use this rule 1, 2 and 3 and arrange this in the increasing order of the energy. So using Hund's rule, you need to arrange this possible term symbol for D2 configuration in a higher energy ordering. Now as you know, D2 configuration is for titanium element where there are two unpaired electron in a d orbital. So that is D2 configuration. So for D2 configuration, possible term symbols are this many and we need to arrange them in the order of energy. So arrange this term in increasing order of energy using Hund's rule. That is for your self-study. Now to the method to decide the ground state term symbol. How we can decide the ground state term symbol for different atom or ion, element or ion. So for that, ground state term can be obtained using LS coupling. LS coupling is also known as RS coupling. RS coupling is also known as Russell-Sanders coupling, which already we have studied in our part 1, the LS coupling. First rule for the ground state term, to decide the ground state term, first point, first of all, to obtain the ground state electronic configuration for any particular atom or ion. Then we need to decide the unpaired electrons arranged in such a way that it should give maximum value of S, means electron should be arranged with parallel spin, and with that its M subside L value would be maximum positive value. Now when I say this, you are not able to understand, but I am going to put the example for that. Let's see carbon, Z is equal to 6. For carbon element in atom form, the ground state electronic configuration is 1s2, 2s2 and 2p2. So here you can see 1s2, 2s2 and 2p2. So there is one unpaired electron over here and the other unpaired electron is over here. And in our part 1 we studied that there are so many possible way to arrange this electron into this degenerate valence outermost orbital of carbon element. Here M subside L value +1, 0 and -1. So we need to arrange the electron, unpaired electron, in such a way that the M subside L value would be maximum positive value. Therefore, we have arranged one parallel electron in +1 and one parallel unpaired electron in 0. But we haven't arranged any unpaired electron into -1 because our rule says that we need to arrange the unpaired electron in such a way that the M subside L value would be maximum positive value. So here maximum positive value we get +1, then after the maximum positive value that is 0, and then after -1 will come. So we have arranged first unpaired electron into +1 and then other unpaired electron into 0, but we haven't arranged any electron into this -1 using this first step. Now the second step for that. Second step is to obtain the resultant L, that is a resultant orbital angular moment quantum number capital L, that will give us the terms. So to obtain the resultant orbital angular moment quantum number L, vector addition of m subside L value of electron is done. What we need to do? Vector addition, sum of m subside L value of electron is done, and on the base of that value L term is decided, and that L term can be decided like this one. If the value of L is equal to 0, 1, 2, 3, 4, 5 and 6, we can assign terms like this one: S, P, D, F, G, H, I, that way. So for 0, L's value 0, we can assign term S. For L value 1, we can assign term P. For L value 2, we can assign term D, and so on. So that way we can get the value of L from the vector addition of m subside L value, and using that value we can assign different terms here. As again you cannot understand here, I need to put example for that. Let's see here the example of carbon here. The L value can be obtained from m subside L1 plus m subside L2 plus m subside L3 and on so on. So here we can see plus 1 into 1 electron. Plus 1 may we have arranged a 1 electron. So I put plus 1 into plus 1. In 0 I have one more electron. So in 0 I put 1 there for 1 electron. Plus for minus 1 I haven't any electron in the configuration. So for that I put 0 here. So 1 into 1 plus 0 into 1, that is 0, plus minus 1 into 0, that is 0 as well. So I get value for capital L as 1, and for 1 value of L1 we should assign term P. So here term should be assigned as capital P. So we have decided the term. Now step 3, that is to obtain the resultant S. Here S is not a term symbol S. Here S is a resultant spin angular moment quantum number. Here n is equal to number of unpaired electrons, and in P2 configuration number of unpaired electron is 2. So if we will want to take the value of S, that is equation n by 2, where n is the number of unpaired electron. Here the number of unpaired electron is 2, and 2 divided by 2 sorry, that is 1. So the value of S is equal to 1. Now using that value of S, we can calculate the spin multiplicity using this equation. So we need to substitute the value of S1 into here. 2 into 1, that is 2, plus 1, that is 3. So we're going to get the spin multiplicity, that is 3. That means this state is a triplet state. So the term should be written as triplet P. Now step 4, to obtain the resultant value of J, that will decide the end step for our term symbol. Using the value of L and S, the value of resultant spin orbital angular moment quantum number J can be obtained through this equation. This is the equation. J is equal to L plus S to L minus S. If the value of J is more than 1, then first point, if the subcell is more than half filled, maximum value of J should be considered for the ground state term symbol. If the subcell is less than half filled, lowest value of J should be considered for the ground state term symbol. And in P2 configuration, we have less than half filled subcell. So the lowest value of J should be considered for ground state term symbol. So this B is applicable for P2 configuration. A is applicable for P3, P4, P5, P6 configuration. For P1 and P2 configuration, this B is applicable. That means less than halfly filled degenerate orbital, lowest value of J should be considered for the ground state term symbol. See, if the subcell is half filled, that is either P3 case or P6 that is completely filled, then J value have only one possible value. So there is no any different value of J, and therefore there is no problem to decide the lowest or ground state term symbol in that case of halfly filled and completely filled subcell. Now here for carbon atom, the value of J should be considered as L is equal to 1 plus S is equal to 1. So 1 plus 1 to 1 minus 1. That means from 2 to 0. That means 2, 1 and 0. These three value we will obtain for carbon atom for the value of resultant spin orbital angular moment quantum number J. But subcell C is less than halfly filled, so lowest value of J is considered, and therefore the ground state term symbol for carbon atom should be considered as triplet P0. Triplet P is already we have decided. Now we need to put the value of J, that is 0, in the subscript, value of spin multiplicity in a superscript, value of L in a form of symbol, and value of J in the form of this lowest value, as it is less than halfly filled. So lowest value of J should be considered for ground state. So here triplet P0 would be the ground state term symbol for the carbon element in its ground state electronic configuration. Now self-study to calculate certain elements and ions and their ground state term symbol. I can give you example of nitrogen, where the ground state term symbol would be quadrate S 3 by 2. How we will going to get this? You need to do the calculation and tell me. If you are not able to do the calculation, please ask me. I will going to explain. This is another example. Sulfur ground state term symbol would be triplet P2. For titanium, it is triplet F2. For vanadium plus 3 ion, the value for ground state term symbol is triplet F2. For chromium, Z is equal to 24. It is quadrate F 3 by 2. For titanium plus 3 ion, it is doublet D 3 by 2. For manganese plus 3 ion and chromium plus 2, because configuration is similar, we are going to get a similar ground state, that is pentate D0. For manganese plus 2 and iron plus 3, because electronic configuration similar, ground state would be exit S 5 by 2. For F3, we have 5D4, penta D4. For cobalt and nickel plus 2 and plus 3, equal electronic configuration, isoelectronic arrangement, we have quadrate F9 by 2 as a ground state term symbol. For nickel plus 2 and copper plus 3 isoelectronic arrangement, we have triplet F4. For copper plus 2, we have doublet D 5 by 2. For copper plus 1, that is Z is equal to 3, Z is 29, that is copper plus 1 cuprous, and Zn plus 2, which is isoelectronic in arrangement, we are going to have singlet S0. So here you can see some p block elements are there, some transition metals are there, and we have obtained ground state term symbol for this using these 4 steps which I have explained you in the early slides, that you may apply and get this value. If you are getting different than this, please let me know. We're going to discuss either through WhatsApp, either through mail, either through any other social media. We're going to discuss this. And if you want to arrange Google Meet, we can arrange Google Meet, and I'm going to explain there as well. Next, that is the method to decide the ground state term symbol. Let me show you that method to decide the ground state term symbol. I am going to show you. Please pay attention to this. Well, you probably have enjoyed this symbolic way of putting the probable arrangement of electron into the degenerate orbital. This unpaired electron will going to generate the microstate. Now we need to study how to arrange those microstate into different energy order and how to decide the ground state term symbol. Please enjoy this another video for the symbolic presentation or to decide the method for ground state term symbol as well. Let's see this symbolic presentation. Enjoy it. Thank you very much. I expect you might have enjoyed this symbolic presentation to decide the ground state term. Now let's discuss. If you are not able to understand this, we have another way to learn this one as well, and that is a concept of pigeonhole principle diagram. Now, how we can study this pigeonhole diagram, probable arrangement of electron into different microstate, and to assign terms to each microstate, we are going to use this pigeonhole diagram. So let's see what is the pigeonhole diagram. Here you can see the pigeonhole diagram is given for P2 configuration. So it is the pigeonhole diagram for P2 configuration. Here M subside L value is given +1 0 -1, and here the spin of electron is given spin alpha spin, that is upward spin, parallel beta spin, that is downward spin, anti-parallel spin arrangement, and here the anti-parallel paired spin is there, anti-parallel unpaired spins are there. Here the value of M subside L, M subside S, and M subside J value is going to be given as well. Now let me explain you the pigeonhole diagram. Here, like pigeon is keeping into different position, here we are keeping electron into different probable arrangement. When you study microstate, you have learned there in part 1 presentation how to calculate microstate or probable arrangement for P2 configuration. You might have studied there are the for 15 different probable arrangement for P2 configuration. So first column will be the first probable arrangement, second is the second probable arrangement. So 1 2 3, let me show you again in a proper way using this. This is one column, first arrangement, second arrangement, third arrangement, fourth, fifth, sixth, seventh, 8, 9, 10, 11, 12, 13, 14 and 15, and this 15 arrangement have different 15 value of m subside L. So here you can see one electron in +1, the other electron in 0. So the value of m subside L, that is a resultant orbital angular moment quantum number, that is +1. But the electron is having a parallel alpha spin, and alpha spin, that means +1. So m subside S value would be +1. mj value is the addition of ml plus ms, that is +1 plus +1, that is +2, and that way we're going to arrange this value of m subside L and m subside S, and for each unique arrangement we have each specific term symbol to assign this. But this is going to be little more complicated and difficult task. Here you can see that all the parallel arrangement is given a blue color. Here that is violet color for all beta spin arrangement. Here one is alpha, the other one is beta. One is alpha, other one is beta. One is alpha, other one is beta. For that green color is assigned, and reverse that for pink color is assigned, and for anti-parallel paired arrangement I've used brown color, and that give rise to m subside L and m subside S value, and from this m subside L and m subside S we can get the value of m subside J. But this will going to give us a very complicated arrangement, and for each individual case we need to calculate and get an assigned term symbol. That is going to be more work for us. So to reduce your work, I would like to give you another pigeonhole arrangement, that is this one. Here this arrangement gives us very easy way to calculate the term symbol, and we can assign for similar microstate. A similar degeneracy is there, then similar term symbol should be assigned to more microstate. So this way we can do the calculation of assigning microstate term symbol to different microstate quite easily. Say for example, here I have taken anti-parallel arrangement, then one alpha, other beta, one alpha, other beta, one alpha, other beta, and then paired up again. So it's going to create a complete cycle, and for that I have different value of m subside L, that is +2, +1, 0, -1, -2, and I give blue color to it, and the box color is blue as well, and that will give me the value of m subside L value, that is +2, +1, 0, -1, -2, and each carrying electron, 2 electron in each case. So the value of resultant orbital angular moment quantum number for these 5 different arrangement, 1, 2, 3, 4 and 5 arrangement, is going to be 2. So we can assign term D to all these 1, 2, 3, 4 and 5 arrangement. We can assign one term, that is D, that is similar for all these 1, 2, 3, 4, 5, that is +2, +1, 0, -1, -2, all these 5 arrangement, that is a similar term, that is D, we can assign. So that is why this different arrangement is given over here. Now for this arrangement, you can see here the electrons are anti-parallelly arranged, either in a paired situation, either in an unpaired situation. Anti-parallel arrangement is there for this m subside L value. So for that, m subside S value is going to be 0. As a result of that, this resultant spin angular moment quantum number, capital S, is going to be 0, and if that value is 0, then spin multiplicity equation, where we can put this S value, substitute this S value over here, then 2s plus 1 is going to be 1. That means it is going to be singlet. So the term is considered as singlet D for all these 5 arrangement, 1, 2, 3, 4, 5. Our m subside S value is 0. So S value is 0. As a result of that, spin multiplicity is 1. It is a singlet. So singlet D is there. For m subside J value, we have L plus S. That means +2 plus 0, that is +2, +1 plus 0, that is +1. So whatever m subside L is going to be your m subside J value, and that is +2, +1, 0, -1, -2, and for that J is equal to 2. So our term is going to be singlet D2, and that singlet D2 term can be assigned to this 5 microstate. 5 arrangement, 1 2 1 arrangement, second arrangement, third arrangement, fourth arrangement, and fifth arrangement. For this fifth 1 2 3 4 and 5 microstate, we have similar term symbol, that is singlet D2. Now here another case is there. In this case I have used blue colored alpha spin electrons. So this is 2 electron p2 configuration, this is 2 electron p2 configuration, this is 2 electron p2 configuration, and for that our m subside L value is +1 0 -1. I have used the green box there, so the green color write up is over here for m subside L value +1 0 and -1, and therefore the resultant orbital angular moment quantum number L is going to be 1. For L is equal to 1, we have symbol P, so term symbol is P assigned to this 3 microstate. M subside S value, because all these 3 arrangement have alpha spin, one arrangement, second arrangement, and third arrangement have alpha spin, so your M subside L value is also +1 +1 +1 -1 -1 0 0 0. So all these 3 sets, set 1 that is this one, set 2 that is violet, set 3 that is pink. For all these 3 we have these 3 value, +1 -1 0, +1 -1 0. So our M subside S value would be +1 0 -1. So S is going to be 1, and it is common for all these 3 sets, set 1, set 2 and set 3. We have S is equal to 1, and that one value, when we are going to put it here, the spin multiplicity would be triplet. So spin multiplicity triplet would be common for all these 3 sets, set 1, set 2, set 3, triplet P, and triplet P. Because for this 3 set, you can see +1 0 -1, +1 0 -1, +1 0 -1. So your L is equal to 1 1 and 1, and therefore P, and P terms can be assigned to set 1, set 2 and set 3, and term is going to spin multiplicity is common, that is +1 +1 +1 0 0 0 -1 -1 -1. So for all these 3 set, your spin multiplicity would be triplet. So triplet P, triplet P, triplet P. Now value of J is going to be changed over here, as you can see in the pink color box, +2 +1 0, pink color box, -1 -2. So +2 +1 0, -1 -2, all is in the pink color, and here it is in the pink color as well, and for that J is equal to 2. So for 5 terms, which 5? 1 2 3 4 and 5, this is not considered. 1 2 3 4 and 5 microstate, your term symbol is triplet P2. Now here the J value is shown in the sky blue color, so that is the sky blue color over here, that is +1 0 -1, and for this 3 our J value would be 1, and for this 3 term, 3 microstate, 1 2 and 3, one arrangement, second arrangement and third arrangement, this third arrangement, second arrangement and one arrangement. So for that we have J value +1 0 -1, so J is equal to 1. 3 terms of triplet P1 should be assigned to this and this microstate. 1 2 and 3 microstate, triplet P1 should be assigned. Now here you can see for +1 0 -1, M subside L, brown color is used, here orange color is used, now this is brown color is used. For that L is equal to 1, term is P, spin multiplicity that is common, that is triplet, so triplet P is there. Now MJ value, that is green, is assigned to here, MJ, that is J value 0, M subside J value is 0, for that J is 0 as well. So for this single microstate, we have to assign triplet P0 single term, right? So when we do the calculation, let me arrange this last set as well. For that, M subside L is 0, so L is equal to 0, term is S, M subside S, anti-parallel arrangement, spin is 0, it is singlet, and therefore term is singlet S. And for M subside J value 0, so it is singlet as 0, and it is assigned to single microstate only. Now let us consider this calculation. 5 plus 5, 10, and 3, 13, 13 and 1, 14, 14 and 1, 15. So total 15 microstates are there, and 15 term symbol we can assign like this way. For first 5 we have 1d by 2. For other 5 we have triplet P2. For other 3 we have triplet P1, and for other 1 we have triplet P0, and last one we have singlet S0. And that way we can assign different term symbol to each possible microstate, each possible arrangement in P2 configuration. So this is the pigeonhole diagram of P2 configuration, and from this pigeonhole diagram we can assign terms to certain degenerate arrangement. These are called degenerate set of arrangement. For that we have singlet D2. This is triplet P2, that is for this 5 degenerate set of microstate 1, 2, 3, 4 and 5. For that we have triplet P2, and for this 3, that is 1, 2 and 3, we have triplet P1, and for this single we have triplet P0, and for this single we have singlet S0. So 5 plus 5, 10 plus 3, 13 plus 2, that is 15 microstate. 15 term symbol should be assigned in this way, and then by applying Hund's rule you can arrange this microstate into increasing order of energy. Now here another case is the pigeonhole diagram for D2 configuration. So here for D2 configuration, that means in a transition element, titanium plus 2, we can get this D2 configuration, and for that we have two different arrangements. This is the first arrangement of that, and here the spin is parallel spin of electron, that is alpha spin. You can see from this to this arrangement all alpha spins arrangement of electrons are there. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 arrangement is there. For 10 arrangement we have all these 2 electron system, that is D2 configuration, 2 unpaired electron in D orbital, and this is D orbital, that is plus 2 plus 1 0 minus 1 minus 2, that is 5 degenerate orbital. In this kind of parallel spin have this many probable arrangement. This is only parallel spin is considered. Anti-parallel we have another pigeonhole diagram for D2 configuration. So D2 configuration have two tabular form. One is for parallel spin, other is for anti-parallel spin. In P2 configuration, in the above slide, we consider parallel and anti-parallel together because only 15 microstate we need to calculate. Here 45 microstates are there. So two probable arrangement is there. One is parallel spin of electron where M subside S value is plus 1, and that when we are going to put here we get triplet value. So spin multiplicity is triplet, that is common for all these 10 probable arrangement, and this 10 probable arrangement will going to give us how many microstate. Let us see. Red colored box is given here, that is for plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3, that is for red color. So here red color is symbolized here for M subside L value, plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3, and for that the resultant orbital angular moment quantum number L value is 3, and for L3 the term is assigned as F. L0 that is S, L1 that is for P, L2 that is for D, L3 that is for F. So here F is assigned to L is equal to 3. Now M subside S value, you can see it is common for all this arrangement. So triplet is there. So our term symbol would be triplet F. For J value, you can take L plus S. Now L is equal to 3, S is equal to 1. So from L plus S to L minus S. So 3 plus 1 that is 4. and 3 minus 1, that is 2. So 4 to 2, that is 4, 3 and 2. 3 j value is possible, and for that three different term set symbol or three set of term symbols would be there: triplet F4, triplet F3, triplet F2. For triplet F4 we have 5 arrangement, 9 arrangement. For triplet F7 we have 7 arrangement, 7 microstate, and for triplet F2 we have 5 arrangement. How this is 9? Plus 4 plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3 minus 4. So total 9 microstates are there for this j value. For this j value, plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3, that means 7 arrangement, 7 microstate have this set of term symbol. And for this triplet F2 we have plus 2 plus 1 0 minus 1 minus 2, that means 5 arrangement is there. So total 21 microstates have these 3 term symbol. This term symbol assigned to 9 microstate, this term symbol should be assigned to 7 microstate, and this term symbol should be assigned to 5 microstate. Total 21 microstate have these 3 set of term symbols. Now here you can see in a blue color, that is plus 1 0 minus 1 m subside L value. So the resultant orbital angular moment quantum number L is equal to 1. So term is going to be your P, and as a result of that m subside S value, that is common, as you know, that is plus 1. So triplet spin multiplicity would be triplet, and as a result of that triplet P is there. Hence j is equal to plus L2 minus L, that is 2 plus 1, that 1 plus 1, that is 2, to 1 minus 1, that is 0. So 2 1 0, that is the 3 different value for j, and the terms would be triplet P2, triplet P1 and triplet P0. Triplet P2 have 5 microstate, plus 2 plus 1 0 minus 1 minus 2, 5 microstates should be assigned triplet P2. Triplet P1, that is plus 1 0 minus 1, so 3 microstates should be assigned triplet P1. Triplet P0, so only 1 microstate should be assigned triplet P0. So 5 plus 3 plus 1, total 9 terms would be there. 21 is over here, 9 is over here, so 21 plus 9, total 30 microstate have this 6 set of term symbol. 30 microstate of D2 configuration should be assigned this 6 set of term symbol, that is triplet F4, triplet F3, triplet F2, triplet P2, triplet P1 and triplet P0. So out of 45, 30 microstate should be assigned with this set of these 6 term symbols. Now let us see anti-parallel arrangement. This is anti-parallel spin arrangement, that is beta spin for this D2 configuration, and for that m subside S value is 0, and that when we substitute over here, it is going to give a common spin multiplicity, that is 1, that is singlet. So for all this arrangement we have singlet term symbol. Now let us consider this arrangement: parallel arrangement, then unpaired, 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 then parallel, unpaired, 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 then parallel, unpaired, unpaired, then parallel, unpaired, and then parallel. So total possible arrangement of anti-parallel spin has been arranged in this way, so that we get this value of m subside L value. You can see how many sets are there. One in orange color, the other is in sky blue color, and the third one is in red color. So let's start with the orange colored set, that is plus 4 plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3 minus 4, that is in orange colored box, and that for that we have taken m subside L value, that is plus 4 plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3 minus 4, and therefore the resultant orbital angular moment quantum number L is equal to 4. Therefore the term should be assigned, that is capital G. For m subside S, because anti-parallel arrangement entirely in the table, m subside S value is 0, so S is equal to 0 as well. hence the spin multiplicity would be 1. So the term should be written as singlet G. Now here the value of J would be written as L plus S to L minus S, and therefore only one possible value is there, because L is equal to 4, S is equal to 0. So 4 plus 0 to 4 minus 0, only one possible value of J would be there, that is 4, and therefore the term would be 1G4, and that 1G4 should be assigned to plus 4 plus 3 plus 2 plus 1 0 minus 1 minus 2 minus 3 minus 4, total 9 microstate. We can assign this one set of term symbol. These are similar microstate having same term symbol, that is 1G4. Now here blue color, that is plus 2 plus 1 0 minus 1 minus 2. So that is shown over here. M subset L value plus 2 plus 1 0 minus 1 minus 2. Hence the resultant orbital angular moment quantum number L is equal to 2. Therefore the term should be assigned is capital D, and as you know, anti-parallel set of spin arrangement is over here. So M subset S value is 0, hence S is equal to 0, so the spin multiplicity would be 1. Therefore the term should be written as singlet D, and here the value of J would be L is equal to 2 and S is equal to 0. So 2 plus 0 to 2 minus 0, only one possible value is there, J is equal to 2. So the term would be singlet D2, and that can be assigned to plus 2 plus 1 0 minus 1 minus 2. 5 microstate should be assigned the same set of term symbol, that is 1 singlet D2. Then after the last case, that is 0, color is not going to be changed over here, but you need to consider this one as a red color. I put it here, the pointer, that pointer color should you need to consider for this M subset L, that is 0, only single arrangement is there. So L is equal to 0, resultant orbital angular moment L is equal to 0, term is going to be S, and therefore you can see here in this arrangement also anti-parallel spin is there. M subset S value is 0, hence S is equal to 0, so the spin multiplicity would be 1, and therefore the term is written as singlet D. It is singlet S, sorry, D is typological mistake, it is singlet S you need to consider, please, I beg your pardon, it is singlet S you need to consider over here. J value would be L plus S to L minus S, 0 plus 0 to 0 minus 0, hence only one possible value of J, and the term symbol would be singlet S0. As I've said, you need to write S over here, singlet S0. Here I have mentioned S, but here I forgot, it is a typological mistake, it is singlet S, and term would be singlet S0, and 0 should be for only one microstate. Now let us consider 9 plus 5 plus 1, that is total 15, and for parallel arrangement 30 is there in the above slide, anti-parallel arrangement 15 is there here, total 45 microstate for D2 configuration. We have assigned different set of term symbol to this 45 microstate of D2 configuration, and that you can arrange into increasing order of energy using Hund's rule 1, 2 and 3. Well, this is enough from my side. Thank you very much for paying attention to this video lecture. After this video lecture, if you have any query, any doubt, feel free to ask me. We can arrange even a live Google Meet as well for this. And if you have individual any question or doubt, feel free to ask me anything. As you know, asking question is a beautiful way to gain knowledge. Thank you very much.